Hi, everyone. Thank you for attending this session. I hope everyone stays safe and healthy in this uncertain COVID-19 situation. Uh, a brief introduction about myself. My name is Meng Lei, and right now I'm working as a software engineer on the infrastructure team at Houzz, mainly focusing on the Flink infrastructure and its applications, also responsible for the mobile data engineering efforts. In this session, I will talk about how the journey at Houzz adopting Flink as our major near-real-time computation engine. And for the people who are not familiar with Houzz, Houzz is the online leading platform for home remodeling and design, which provide a platform for the homeowners to shop products, find professionals, get design ideas by browsing millions of photos. And also it provides the software for the professionals to grow and manage their business. Here is today's agenda. First, we'll talk about the setup of Flink at Houzz and the data challenges we are facing. Then talk about how we use Flink to power our event pipeline. Then share two interesting use cases. The first one is the personalization pipeline for our home feed, and the other is Kubernetes logging observability. In the end, I will talk about the lessons we learned from Flink on Kubernetes and the future work we plan to work on. A few stats about our Flink clusters. At the very beginning of this year, we adopted Flink, and within several months, we successfully productionized more than 15 jobs by partnering with different teams from different verticals. Also, we deployed our Flink on Kubernetes and use our internal monitoring infra to do the monitoring, such as using Prometheus and OpenTSDB and Grafana, etc. Also, right now, the data volume is more than 10 terabytes per day. And here is a brief overview of our data pipeline without Flink to demonstrate the data challenges we are facing. So in a very high-level view, we have two types of the pipelines. The first one is the log shipping pipeline. In this case, this is our source of truth for the data warehouse. And the top priority is the data accuracy and completeness. In order to achieve that, we have built some systems around it to do the data auditing, validation, and recovery with some metadata storage. On the other hand, different teams can develop their own events and define the schema and using tools such as the Kafka Consumer or the Spark to implement their own business logics managed by themselves. As our business grows, we do encounter more issues such as the operational cost and touching the legacy code base. What we do want to have is to have the ability to leverage our logs for the streaming app. However, the log is designed for our data warehouse, so sometimes the schema is pretty normalized and it cannot achieve our goal. Eventually, we adopt using Flink to provide a unified pipeline across different verticals. Our goal is to make it log once and used anywhere. And here is how we approach it. Basically, we implemented a Flink event hub to do the processing for our raw logs. After our highly nested log arrives the Flink, we apply different processors for different stages, such as the bot processor, user identity check, user data enrichment, deduplication, filtering, and joining. And then split the dispatch and split the logs into different streams, and eventually send it to dedicated Kafka topics. And we just take a look into two processors. The first one is the multi-stage event data enrichment. For our data, for example, the tracking pixels or the mobile data, sometimes it could arrive in late, or the data is highly normalized. For example, it only contains the visitor ID, even for the user session, and then the data warehouse will do the rest of the job. But in this case, we want to do it in real time. So we approach it by joining with the events with the same session. For example, join with the login session, and then do some data ETL to enrich the data in real time, so that we do a good job to enrich the more than 98% of the events, and also maintain a pretty low latency in 95%. Also, in addition to that, we do have some various data which is not qualified, and due to various reasons, for those data, we do the template window and async call to query and batch to query our external DB or the cache layer to get a pretty measurable P99 latency. The latency here is our latency, and the accuracy is our top priority here, since this is pretty critical for the downstream job to define their window and watermark. In addition to that, we have a event deduplication processor. We try for our nature of the pipeline, it has some duplicates by design, and however, some data apps cannot accept any duplicates. In this case, we tried different solutions. Eventually, we found out that using the local RocksDB with SSD and using background compact filter is good enough to solve our business needs. Then let's talk about one interesting use case, which is our personalization pipeline to power our home feed. When we talk with the personalization team, and here is their goal for their near real-time pipeline. They want to do the session-based recommendation and the user interest aggregation and clustering. Eventually, they want to unlock the ability to do the user intention prediction and reinforcement learning feedback signals generation. If we translate it into the Flink requirements, we figured out that it's more like a balance between the lagging and the data quality. For the short lagging jobs, we just do some lightweight and fast incremental computation, and solve it internally as a state. And for the long lagging jobs, which means that we have more data to play with. So in this case, we can build some sophisticated sequence flow, and then call some remote services to do some slow and expensive computation. For example, some high CPU or GPU bound computation. Also leverage our history logs in the event data lake. Here is an example of the whole how the data flow works. After we get the raw events from the data hub we mentioned before, we first do the first level of data enrichment, and then apply the windows with different granularity. For example, for the windows in seconds, it can do it within the state and eventually log it in the key value store. On the other hand, we can apply some longer window and define the watermark aligned with our latency in the event hub to do some more complicated computation by calling our machine learning servers. Eventually, we log this data in our key value store as well. In this case, we use Redis and Elasticsearch as our key value store. The Elasticsearch also contains our user profile data to power our user profiling service. So this data can be a piece of data for that purpose as well. After that, we have the recommendation servers to use this data as one part of the source of truth to do the online recommendation serving. On the other hand, after we get the data sequence, we do more processings like the hourly rolled up with some window sliding, so that we can get the sequence flow and log it in our sequence storage. In this case, we use Cassandra. And this data will be another reference for our machine learning infra to do the model training and testing. So in this case, we do want to be aware of that the latency is pretty critical here, because if anything happened in the upstream, it could have some bad impact to our pipeline. So we have to define our watermark carefully with some threshold. Then let's talk about the Kubernetes logging observability, because at Houzz, after we adopted Flink, we found out that it not only help us to build the different pipelines for our business need, it can also help us support some pinpoint in the DevOps front. And in the middle of this year, we successfully migrated 100% of our user traffic to Kubernetes. And in order to support it, we have ability to an opportunity to rethink and design the whole logging architecture. And here is some requirements. As you may know, for the observability, there are 3 pieces: tracing, metrics, and logging. For the metrics, we use the Prometheus, which provide a very good ability to do the joining by the Prometheus SQL. But for the logging, we use Elasticsearch plus Kibana. However, in order to support our 100% user traffic and all engineers debugging in real time, we do need to provide some good user experience. However, the Elasticsearch itself does not support join, so we need to join the data within the Flink, especially in the Kubernetes cluster environment. At that time, we have some comparison with other solutions, such as traditional Logstash or the Flink, but they have their own limitations, such as the performance issue and for the Logstash and no real cluster mode for the Flink. And here is the whole architecture. As you can see, there are various workloads on our Kubernetes cluster. And the way we collect the log is a combination of the sidecar and daemon set. For the sidecar, it is another sidecar container within the Kubernetes pod, and collect various logs on within the pod disk. And then we have a centralized daemon set to ship all various logs to the Kafka topics. And then we use Flink to do different kinds of processings, such as they share the same common Kubernetes processor, and also they have their own processors, such as the JS processor. This one is pretty interesting because sometimes the front-end JS error cannot be captured easily, and the way to approach it is to process and parse it and generate some highly customized data and log it into our monitoring infra, so that different teams can have their customized metrics and then build the alerting on top of it. Let's do one more case study on the Istio cross availability zone distributed tracing issue. So Istio is our network service mesh layer to do the traffic routing. And sometimes we do encounter something like traffic and imbalance and hotspot. However, sometimes it's not caused by a single reason. So we do want the log to have a distributed view or graph view so that we can monitoring and debugging it in a faster way. And the way we approach it is to use Flink to do the bucket sampling first by the request ID, and then parsing and pairing the source destination pod IP from the log, from the ES2 log, and then do several stages of data enrichment by calling our metric server to get the mapping between pod IP to pod name or the pod name to the AZ and node, so that we can tag in all those data. And here is the visualization of this after we have this. You can see on the left side, it's the traffic distribution among different availability zones. And within each zone, you can see which zones it comes from and the distribution of that source. On the right side, it's a view of a pod traffic distribution within a certain period. One good thing is that you can see it comes from several availability zone, and also you know which node or which pod it comes from. The good thing is that since this is log and there's no data loss, and you can just click the one of the pod and pod on this figure, and you can have a global view of what happens from the access log, debug log, or the error log. And this pretty much helped us to investigate those issues in a very quick way in some critical time period. And here is the use cases I want to share today. And we do encounter some issues and learned a lot from the Flink on Kubernetes. The first thing is that we have to keep all the logs persistent in the stateless environment, especially something like the segment fault or the JVM issue happened. We do want to log all those logs, including the core dump, into our logging infra. The other is manage the resources and the scheduling on Kubernetes carefully. For example, we apply the different node affinity rule to make sure that job manager running stably on the Kubernetes, and also need to configure the pod lifecycle to make it shut down, for example, shut down gracefully. Also, some management on the memory as well. Another is to avoid some hotspot. Since our Flink is running on Kubernetes and shared with other workloads, sometimes the requested CPU is not enough, and it could slow down the whole pipeline, which cause some pretty bad impact on the data quality and logic. So we have to manage those pretty carefully and calculate, and also pay attention to other workloads running within the same node. Also, something like the Kafka topic partition would cause some hotspot, and which affect our watermark and window generation and accuracy. Here is some future work we plan to work on. Since we have already adopted many jobs, and we have to provide more tooling and library support, so that get it easier for the new devs to onboarding to this platform. The other one is to streamline the build and deployment pipelines to make it easier manage and improve the productivity. In a long-term goal, we are exploring the native Kubernetes integration to unlock our possibility for the auto-scaling. Well, I think this is all pretty much about today's session. And if you have any questions, feel free to ask in the Q&A session.